Okay, let's wait until Sophie is here. Well, let's wait one more minute and we will start. Okay, let's start. First of all, let me thank you all for coming here today. My name is Yaroslav Vorontsov. I'm from DataArt Voronezh. I work as a software architect and tech lead in mobile technologies, and today we're going to discuss the topic of mobile application security on iOS. So, what is this? What does it consist of on iOS platform? So, here's the agenda of our today's talk. We will cover the basics of security, some theoretical principles. Then we will move to the discussion of Apple's iOS white paper, the most recent version of it. Then we will go then we will see how an attacker can access the data in iOS applications. Then we will overview the security APIs which help us preventing such kind of intervention. And then I will give you some practical examples, so-called ready-to-use recipes on how to protect particular pieces of data on your phones. And the final part of my presentation would be the materials and links. So let's start. The introduction is, of course, about the theoretical base of information security and basic principles of it. Okay, each newcomer who comes to the information security starts with the probability theory and the concept of negligibility. So the concept of negligibility is the basic one here. If the probability of an event is negligible, it means that it will almost never happen, but it could happen theoretically. This concept is the basic one. It means that it is basic for different encryption and decryption algorithms, as well as for pseudo-random functions such as hash functions. Then the second concept is the pseudo-random number generator. You may know that most of classic generation functions like rand, srand, srand48, they're actually not random at all. We need to provide a so-called seed the initial value of the generator, which will produce all the next values of this function. However, if we provide the same seed twice or more times, it means that these pseudo-random sequences would be the same. It means that the probability of guessing such a sequence is not negligible, and a potential attacker could hack this and find out if the sequence he has built matches with the sequence built on the server or on the client side. The next concept is the pseudo-random function or pseudo-random permutation. Well, the ideal cipher or the ideal hash function produces an output which is indistinguishable from a truly random sequence of symbols. So pseudo-random function is a one-way transformation from the source data to the output, which produces a pseudo-random sequence. Pseudo-random permutation works in two ways, so all symmetric cipher algorithms are actually pseudo-random permutations. Speaking about the symmetric and asymmetric encryption. As I said previously, we have symmetric ciphers like RC4, AS, Camellia, Salsa, and so on. But the first one, which is absolutely cryptographically secure, was one-time pads, introduced by Vernam in 1917. Why is it considered as an absolutely secure cipher? Well, actually, the key which we are using for encryption should have the same length as the open text. We are XORing them and we receive the ciphertext. However, if we use the same key twice or more times, then we could employ cryptanalysis and decode what was the original message and what was the key. So this cipher is absolutely secure only in case we use each key only once, and the key length is equal to the message length. You know that sometimes it is, most of the times it is inconvenient to use such a long keys, so there are different ways on how to extend the existing small keys into the larger ones, like key stretching functions. Okay, apart from using symmetric and asymmetric ciphers, asymmetric are those which use more than one key, usually use two keys, and they are, digital signature algorithm or Rivers-Schemmer-Edelman ciphers. Then, moving on, we could speak about the hashing. Hashing is a one-way function which transfers the existing data, so it is indistinguishable from a random sequence of symbols. And message authentication codes, so-called MACs. If you have encrypted a message, you should send it to the receiver, and the receiver should know somehow that nobody has tampered into that message. No one has added any kind of symbols there. It means that we should introduce a kind of function which allows us checking the hash sum of this message. So we encrypt the message using, let's say, AES cipher, and then we put an additional sequence of hash bytes of this encrypted message. When a receiver receives this message, he checks if the signature is the same that he received previously. If it is not the same, it means that this message was compromised by a malefactor, and we cannot trust the source of these messages. By the way, there are several attacks used on encryption, like empty initialization vector, timing attacks during the comparison of passwords and keys, and so on. We will talk about some of them a bit later. The next point here, which is essential for all developers to understand, is that we are actively using network communications in our applications, so we should protect them as well. And we should know which level of SOC stack or TCP/IP stack is responsible for encryption. Most of the applications use HTTP or HTTPS protocols. So actually we are using the session layer or layer 6 in this model. And we use either SSL or TLS. However, we will have a brief discussion why SSL is not considered secure anymore and why we have to use TLS only. The next point, which is essential for a specialist in information security, is the understanding of key generation and distribution schemes. You may know that there is a common key distribution scheme named Kerberos used in Windows domains. You may be also aware of Diffie-Hellman protocols, which are used in SSL and TLS for the key exchange and for creating a session encryption key. However, even such a scheme may be compromised if we had a man in the middle between our sender A and receiver B. That's why we have so-called lists of trust and certificates. Actually, the certificates are dedicated to asymmetric encryption and to public and private keys. And this is interesting how we can validate an existing certificate and check whether it has been revoked or compromised by a malefactor. And the final point here is the documentation. We have public key cryptography standards, also known as PKCS, and RFC documents, request for comments, which regulate how these encryption procedures, how protocols behave in the World Wide Web. Okay, some terms which I will use actively in my presentation. The first one is the triple letters I, A, and A again. They are for identification, authentication, and authorization. So identification is providing an evidence that you are you. So we can compare it with some kind of face control in a trendy club when you show a security guard your identity paper and he matches your face with that one displayed in your passport. The second one is the authentication. It means that you provide an evidence that you know something secret about yourself and someone validates that this knowledge is valid. Authentication is usually about inputting some passwords or keys into the specific fields. And authorization, it is the check of privileges. After authentication, we may be eligible or not eligible for accessing a particular part of the system. If we are not eligible for that, we will see an error saying that our access to this functionality is denied. Then, two-factor or multi-factor authorization. I think that it is pretty clear what it stands for when we use another factor, which is different from the first one we are using for authentication, whether it is a key, a password, or a token. UID and GID, user ID and group ID, or unique ID and group ID. These terms are used in the iOS security white paper to introduce the specific keys which are special for each device. Then, key wrapping it is a special case of encryption when we encrypt the encryption key. Yeah, some kind of matryoshkas. Key wrapping is also actively used in iOS security white paper, and it stands for the hiding the encryption key by applying another cipher on it. And MDM system, it is a mobile device management system. It's a common system in enterprise when we have, let's say, lots of corporate devices and we need to roll out a common policy on them. Mobile device management could also affect the security policies of a particular device, whether it is a corporate device or bring your own device. So let's move on and have a brief overview of security white paper. The most recent one is available via this link. It is a PDF document containing about 65 or 67 pages. Just for you to be aware that 2 or 3 years ago this document was much thinner and contained only 5 or 10 pages. It means that Apple had put their focus on security really hard. Because of different attacks like Beast, Poodle, like data leakages and so on. They hired lots of specialists in security area during the last 3 years and revised their security policies as well. So that's what they have in this paper. This paper describes the following things: the boot process and system software authorization, then the concept of secure enclave, a co-processor for a 7 ARM processor and above, passcode and Touch ID policies. By default, there are 3 different policies if you have passcode enabled. And we will look that passcode is an essential element of iOS security and iOS built-in mechanisms, protection mechanisms. Then it also describes the AES hardware acceleration. There is a special crypto silicon model which is responsible for cryptography only. Then we will look what data protection classes are available for file system and for keychain items. We will look briefly on the key bags which are available in iOS, and finally we will look through a list of the different security important features. So let's start with the boot process and system software authorization. Each iDevice starting from A7 contains an area named Secure Enclave, and well, all the modern devices have so-called boot ROM. It is an area of memory which is read-only and which contains the initial bootloader code and the Apple's root certificate, so public key. When we press switch on button on an iDevice, the system loads boot ROM and checks the digital signature. So the overall process of boot follows the transaction principle, all or nothing. If one of the steps fails, it means that the system won't load and would ask you to connect your device to iTunes to restore its firmware. I think that most of you have ever seen at least once such a screen, especially some of you who tried jailbreaking your own devices. Then if the first stage has succeeded, then boot ROM gives control to a low-level bootloader, which also checks the digital signatures of firmwares located on the system, and if the firmwares are valid, then the system starts loading the main loader called iBoot. This is where the system software authorization works. During the system update, your device sends a special signature containing of device unique code, so-called ECID, a special non-CE value which prevents this code from being reused once again, and sends a signature of all system components. Then the system receives the signature of the updates and stores them locally. If one of these updates is compromised, let's say jailbroken, then the system would go to DFU mode, and we will see the connect to iTunes message on the screen. And once the iBoot stage is completed, then the kernel is loaded and we have access to the NAND memory, so to the hard disk of the iPhone. What is a secure enclave? As I said previously, it is a security coprocessor which is responsible for different security features, starting from encryption and ending in storing your Touch ID or Face ID. It is available for all modern A7 and above processors and S2 and above CPU family. It contains a built-in hardware pseudo-random generator. It means that such generator has better entropy than a simple one and produces random numbers which are almost indistinguishable from a real random sequence. It communicates with the main central processing unit via mailbox pattern, so it sends messages to a secure area of memory and grabs the same messages from another secure area of memory. All this stuff is managed by hardware interruptions. Secure Enclave is also responsible for passcode, Touch ID, Face ID, and data protection classes. So it's a central element of iDevice protection system. For the newest devices running on A9 processor and above, it also generates the unique ID. That unique ID, which may be seen and damped during the bootloading process on the jailbroken devices. Secure Enclave updates its firmware independently from the base system, and it has its own signatures. and it also generates and stores different elliptic curve cryptography keys. You may know that starting from iOS 9 it is possible to generate self-signed certificates on iPhones only, and the certificates would be non-exportable by default. It means that the private key won't be exported in any conditions because it is contained securely in secure enclave. Let's move on and discuss what are the passcode policies which are provided by the system. System provides us by default with 3 different passcode policies. The first one is the simplest. You provide a 4-digit passcode. Then you could provide a 6-digit passcode and an alphanumeric passcode of an arbitrary length. The longer the passcode is, and the better the quality of the encryption keys is. If you use letters in different registers, if you use special symbols, the entropy is larger and the quality of keys is even more better. To prevent time-and attacks on encryption, secure enclave have a constant interval fixed at 80 milliseconds to check whether the passcode is valid. So when you input this, independently of what the length of your passcode is, you will receive the same time delay. Then there is a special algorithm which prevents the passcode from being being hacked by the brute force. After each unsuccessful attempt, the delay between attempts is enlarged. So after 5 invalid attempts, it may happen that you have to wait for 1 or 2 hours or more. By the way, it is configurable via MDM systems. You can also store up to 5 fingers using secure enclave. You scan them using the Touch ID sensor, and they are stored in the neural network form there. There are also 6 mandatory cases of inputting the passcode, even if your Touch ID is configured. For example, they are having the long inactivity interval in system 6.5 days without entering the passcode and more than 4 hours of inactivity. You may notice that if someone of you has an iPhone with a Touch ID sensor and you have not used it for a long time, let's say you put this device on the charge for the night, and when you wake up in the morning you see that the system asks you for a passcode, not for the Touch ID. Then you should also provide the passcode. This is the second variant. When you failed to provide a valid fingerprint for 5 times in a row. After that, you have to do this. If the wipe policy is configured, after 5 more or 6 or 7 more attempts of providing invalid passcode, the device would be wiped. This number is also configurable, but the common cases are having from 10 to 12 invalid attempts. To say honestly, Touch ID is not so secure because unfortunately special forces in all countries of the world could scan the remains of your fingerprints somewhere and prepare a silicone model of your finger and use it to unlock your device. Face ID is way more secure, but unfortunately it may not work in several cases, or when you have a twin sister or brother. Yeah, National Security Agency may use your sister or your brother to unlock your own iPhone. The most secure way, and by the way, the most secure way even in the United States of America, is having a passcode, because if you have biometric authentication configured on your device, the border officer or the police officer may ask you to unlock your device using the finger, and you have to do that, because otherwise there would be a penalty. If you have a passcode installed, you may not tell him or her the valid passcode because it's your right. So before going to the United States, it's better switching off biometric authentication. What is a crypto engine? It is a special piece of hardware on iPhone, which provides us with a set of encryption keys. So the main encryption key is 835, which is derived of zeros and ones, combined with the unique ID of the device. This key is hidden somewhere in the silicon, but if you patch iOS decrypt function, which is available on the boot in the boot time, in the iBoot bootloader, then you will be able to dump all these keys. Fortunately, the jailbreaks are really rare now because the cost of each jailbreak is increasing because new security features are being added constantly into new devices. It is harder to dump these keys. Unique ID or user ID is unique for a particular device. So each new device after reset generates a unique ID. Group ID is built into the central processing unit. It is an in silicon key, and it is common, let's say, for all A7 or A8 or A9 processors. These keys are not living crypto engine, so as I said previously, the only chance to see them is to find a jailbroken device and dump the iOS decrypt contents. What are the file protection classes? All the files on the file system are protected by default by using some encryption keys. iOS provides us with 4 different protection classes. The first one is the complete protection. It means that files are available only for the application which is in the foreground when device is unlocked. It means that this is the most secure way of storing some confidential information. And the class key is protected with a key which is derived from the passcode and device your unique ID. It means once you've locked the device, this passcode derived key is wiped off from the memory and you're not able to access these files anymore. Once you've unlocked the device, you're able to access these files. The second class is the file protection complete unless open. This is a more relaxed way of working with the sensitive data. It means that some files can be written on a disk even if the device is locked. The common use case is the mail application. Let's say you received a mail with a large attachment. So you've pressed on the load attachment and you went off this application and you suddenly locked the iPhone. When you open your mail application again, you see that the attachment is here. What has happened? The system has stored a special asymmetric key in the memory until the moment of full download, until the moment the download has failed. Once it has been downloaded, the system encrypts it with one of these keys, let's say with a private key. Once you unlock the device, you will have the other unit of this pair, the public key, so you will be able to encrypt to decrypt the contents of the mail's attachment. This behavior is regulated by one-time Diffie-Hellman key agreement, so asymmetric cryptography is employed here. The third class is complete until first user authentication. It means that these files are not available when device is switched off, but they will become available once you've provided the passcode after you boot the device. It is a default class for all third-party applications starting from iOS 7. So our files, if we write an application, all files of this application are not available on an iPhone which is switched off and which has not been unlocked using the passcode. Except the only change with in comparison with the file protection complete unless open is the key persistence. The key is persistent until the reboot. And the final class, it is file protection known. Actually, the files are encrypted, but they are encrypted only using the device unique ID key. It means that if we know this device unique ID, we are able to decrypt all this stuff and find out what is contained in those files. These are 4 protection levels of files. We can use them in all our applications. How this mechanism works? Yeah. Okay, I would recommend never using file protection known unless for some cache files which contain some crap or some open information. I would recommend using file protection complete for files containing sensitive information like user logins, passwords, password hashes, personal medical information, personal banking information, and so on. As for the others, we need to find the balance between complete unless open and complete until user's first authentication. If you have applications which actively use background fetch, then the second variant is your choice. I mean the complete until first user authentication, because these background fetches are scheduled using an SQL session daemon, and you will have to be able to write down the contents of the response you received from the server to the disk, and you won't be able to do that if you have the device locked or your application is not running. That's the case. As for the complete unless open, I've already provided a use case. It is the background download case, when you started downloading foreground and then you went to background to switch to another application, or just to throw the application away from the task manager. So how it works actually? The file content, each file has its own file key, and this file key is included into the file metadata. File metadata is encrypted by using file system key, which is derived from the device unique ID, and also is encrypted and the file key is also encrypted using the file protection class key. So we have 4 different file protection classes. However, class keys are easily can be easily viewed on the jailbroken devices unless you have not set a strong passcode. So as you can see, the quality of the passcode affects the quality of the file system encryption keys. Once you've set a weak passcode, you have the weak level of protection of your files. If you have set a strong passcode, then your data is sufficiently secured. File system encryption uses AES-256 algorithm in cipher blockchaining mode, and well, it also uses SHA-1 hash to generate the message authentication codes, just the checksums to be sure that the files were not changed. When a file is accessed, its key is unwrapped, so decrypted, and this key is stored in memory and used for file decryption, whether it is access to the whole file, loading it, let's say, to the memory, or whether it is a file handle, when we seek to an offset and start decrypting the file. So here are the essential elements of file protection system: file metadata with file key, user's passcode, and device ID. If you have not set the passcode, your data is under the risk. What are the key bags? The key bags are special key storages which contains the file system encryption keys. There are 4 different key bags in iOS by default. The first one is the system. It is always, unfortunately, it is always accessible. Otherwise, we won't be able to decrypt or encrypt something. However, it is stored in silicon ineffaceable storage, and it is harder to access this rather than dump the memory or view it somewhere else. The second one is in iTunes backup. This key storage duplicates the system when you are creating a backup. However, it can be additionally protected if you provide a special backup password. If your device is configured via an MDM system, it means that you can set a mandatory password for backups, and it means that the second keyback would be sufficiently protected. The third one is the escrow keyback. This is the keyback which is stored in MDM system itself to allow remote installation and removal of software. If you haven't had such a keyback on your MDM server, you wouldn't be able to install any software remotely. And the fourth one is an iCloud keyback. It contains your iCloud backups, and since it is a compromisable storage, it uses asymmetric cryptography. So one part of the key goes to the cloud, the other remains on your device. It means that the data decryption key goes with your backup, and the data encryption key goes with your backup, so you will be able to provide some incremental updates, and the data decryption key is contained on your device only, so no other device could be restored from such a backup. This is how iTunes backup keyback works. We have a backup password, we have a backup keyback, which is encrypted using file encryption key and a special initialization vector. And we have the final key to decrypt the whole backup.
Excuse me,
Yeah.
I want to back up a little bit about the file with the file system encryption.
Yeah.
So the files are basically always encrypted.
Yes.
You access them, and depending on the policy, they might be.
Yeah, depending on the the only difference between this encryption mechanism is the policy, how the actual file encryption key is encrypted, how it is wrapped. So the most securely wrapped keys are for complete protection level. The least protected are for known, so they are not actually wrapped using the third-party source of entropy, using only system provided keys.
And I guess the files are decrypted in memory.
Files, yeah, they are decrypted not in memory but in secure enclaves memory. The file contents are run through the AES decryption and encryption engine, so you just have a black box. You feed some data there, you feed an encryption key if it is not contained already in the secure enclave, and you receive the stream of bytes of decrypted files. So as I mentioned earlier, keys are not leaving the secure enclave if they are contained within it. Okay, what other features do we have which are built in? Sometimes we even don't put any attention on them because they are usual for us. The first one is code signing. It prevents us from running any unauthorized code. iOS checks digital signatures of the files. If you're registered as an Apple developer, then your personal certificate is signed using the Apple's certificate's private key. And system knows the public key of this Apple certificate, so it will be able to validate your digital signature on the code you've produced. Then, the second concept is the sandboxing. It means that all applications are isolated from each other. Each application has its own sandbox, its own small model of file system, its own area of memory. The third one is the least available privileges. You know that Unix systems are multi-user by default, so it is possible to run applications under different user accounts. So the account with the least available user privileges, which are sufficient for application running, is used. For third-party applications, system applications use a little bit different levels of access, but it is not the case for our presentation. The entitlements mechanism. They regulate the access to some hardware features like Bluetooth, like camera, like microphone. They also affect how push notifications work and so on and so forth. Then the ASLR, or Address Space Layout Randomization. It is a mechanism which is built into the kernel, and it prevents a library from being loaded to the same base address. You know, there were lots of articles saying something like smash and stack for fun and profit, so how to exploit an application. They were based on the fact that the application is loaded into the same memory address each time it is being run. However, in the modern operating system, ASLR is switched on by default, and it prevents the attacker from guessing the base load address. Execute never flag or exend flag. In IRM systems, all memory pages are non-executable by default. Only those pages which pass the code signing step, which contain the executable code which has been signed by a valid profile, are executable. Access limitation, it is a well-known feature. We should provide the reason why we do need access to camera, to contacts, to microphone, to Bluetooth, and something else. If user doesn't give us an access, then we're unfortunate. And extensions. I mean keyboard extensions, watch extensions, and so on. They inherit the rights, the access rights from their basic application. However, there is an exception, which is not mentioned here. It is the keyboard. Keyboards are actually extensions of the apps, but they run with the lowest available privilege level. They are working in a set box which is isolated from the network. Otherwise, you know, there would be lots of keyloggers on iOS. A brief explanation how SLR works is available on the right part of the slide. The first start, okay, unfortunately this is a screenshot for Windows. I haven't found a sufficient screenshot for Mac or for iOS. So we could see the GDI library is loaded first on the first stage, then it is loaded somewhere in the middle, and finally it is loaded somewhere else in the end. So all the libraries are mixed. They have different base load addresses from start to start. The left part of the slide contains the explanation of executable PIE feature. It is a feature of compiler which switches on ASLR on iOS. As we can see, if we disable this PIE flag in the system's kernel, then we are vulnerable to exploits. Otherwise, everything like main executables address, heap address, stack address, shared libraries address, and base link address are randomized, absolutely randomized. So, but how could we breach into an existing application? This is a small section describing how and what are the attack vectors. This is built according to a WASP cheat sheet for a penetration tester. You can scan the link and find out what it says. And you could see the following image, this explaining the main vectors of attack here. So, what does a security assessment of an iOS application involve? It involves application mapping, like exploring what features are available in the application and what are the data flows, whether we could interfere in that flow and inject some code or some data which might compromise the system. Then client attacks like binary analysis, memory patching, and file system research. Then network attacks, which are the most popular when we are becoming a man in the middle between the iPhone and the server. And server attacks when we are trying to use the compromised API to send malformed packets or try to interpret some data as a command. What are the tools? What is the toolkit of a penetration tester? First of all, it is a proxy server like Charles, Burp Suite, what else? As far as I remember, there were lots of them, like Fiddler for Windows and so on. The second is the OpenSSH console. Once you've jailbroken your device, you're able to start an SSH daemon on it and connect and view what are the processes here. You will have the full Unix console on it. The third tool is an SQLite database browser. You can use the pure SQLite web console or use tools like Valentina Studio, Leah, or DB browser for SQLite to view what are the contents of DB files and SQLite files. The fourth is the GDB or debugger. It is used to decrypt the App Store encrypted binaries, to load them into the memory and to dump them on a disk to have an decrypted binary for the further analysis. Then you could use OTool. It is a binary information extraction tool, or you just use linker. Then manage kernel parameters using sysctl and switch off ASLR, for example. Then you may use scrypt, pseudo JavaScript language, which allows you patching memory, patching system methods, patching application methods. You could also use some specific proxies like retools or Mallory for non-HTTP connections. And finally, you could also use Wireshark to track the HTTPS streams and TCP or UDP encrypted streams. This is what I'm using in my work as a penetration tester. However, how can we protect our data? Or how can we reduce the risk of being hacked? Here are some APIs which we have. So the first thing which you may learn from each information security course is do not ever try implementing encryption by yourself. This is the worst idea which may happen in the world, because you're reinventing the wheel and your implementation is vulnerable to common attacks which are already known and which are theoretically known. As you may remember, we've talked about the negligibility concept, so why it affects the encryption. Even if a cipher is theoretically vulnerable, it should be thrown away. Why? The computational power is growing each year, and attacks which were theoretically possible 2 years ago are now practically possible. So each theoretically compromised cipher or encryption scheme should not be used in production. Lots of encryption algorithms were removed from the official SSL suites and are not supported by Apple as well. The only algorithm which is used for traffic encryption, I mean the symmetric crypto algorithm, is AES. We will see that. Okay, we have the security framework. It is a pure C API. We have several parts of security framework, and they are namely the common crypto library, which contains all the crypto algorithms and all the hash functions. Usually these functions and algorithms has CC prefix. Then we have the keychain API. It is a secure storage for credentials. We have the certificate management, like SEC certificate and SEC trust functions. We may use these functions to modify the default behavior of the HTTPS stack. And some SSL 3.0, TLS 1.0 connection management. These functions should not be used because both SSL 3.0 and TLS 1.0 have been compromised. As far as I remember, there were attacks like Heartbleed, Beast, and Poodle. They are theoretically possible, but some of them were practically employed by using huge data centers. What is a keychain? A keychain itself is an SQLite database which contains the encrypted contents of the items you've marked as secure. It is designed for passwords, for tokens, for certificates, for public and private keys, and everything else which is related to key and code and receipt management. By the way, it also could be used for data sharing across the applications, but it requires a specific feature named access group, and it requires configuring your application profile on the Apple developer and providing a file with entitlements containing keychain access group, application identifier, and application group. Fortunately, this feature works only for the applications signed using the same team ID. If team IDs are different, but the rest of the applications identifiers are the same, this won't work. Otherwise, we would have the situation when everyone could, let's say, use the bundle like Microsoft Office and store all your credentials from Microsoft Office or from Outlook. The keychain works outside of the applications via keychain daemon, and it works via secure enclave on the majority of modern devices. How it works? Actually, you do a special request, then it is transferred to the security API, which searches the keychain using a special identifier and passes the data to the secure enclave. Secure enclave uses the keys contained in it and decrypts the contents, and if decryption is successful, it returns the secret data to the keychain API, and then you have the decrypted password or the decrypted license key. How we can view this? For example, this is a dump of real jailbroken device, and there are several generic passwords there. Most of them are related to system facilities, to system applications, but as far as I remember, okay, here's one more account related to Wi-Fi, which I used during the penetration testing session. What is encrypted in a keychain item? The first of all is label, so-called identifier. A key itself, well, a real key has a label itself. So this is what you're using during the search. The key itself is hidden and encrypted. Once you've asked for that, the system decrypts the key and gives you the full keychain. The system also encrypts the timestamps of last access and the creation date, dictionary of different attributes, whether it is a generic password, internet password, whether it is a certificate or something else, and the keychain content, the keychain item content itself, the password, the certificate, and so on. It is also essential to store the service of the application which uses this item to support keychain sharing. You see that it is identified by reverse DNS style labels like com.apple.certui or something like this. Keychain items has also different protection classes, and there are some specific protection classes which are not available for file system. Okay, I will try to provide an equivalent of the file system protection class for each keychain class. When unlocked, it is equivalent to complete protection, so you won't be able to access this item unless your application is running in the foreground. The next is available after first unlock, matches to the until first user authentication. Then accessible always. It means that it has no additional protection attributes, and accessible when passcode set this device only. Well, this is a difficult label which explains a very simple concept. If you marked a keychain item as this device only, this won't be restored to any other device if you are using an iCloud backup or an iTunes backup, because this item is encrypted using device-specific 835 key, so it won't be decrypted correctly on all the other devices. It means that this item is not migratable and it won't be synchronized via iCloud. Sometimes it is useful to have a local storage only for some security critical or security essential keys. How can we share data via keychain? We just configure our entitlements, adding keychain groups, and allow keychain sharing. Then we should go to the Apple Developer Portal and configure keychain sharing. As I said previously, the same team ID is required. So if you have two different team IDs or two different teams in the App Store, you should use the same team for distributing this application. It is interesting to mention that some keychain items are accessible by Safari, starting from iOS 9. And you could use password generation functions on iOS 10 and iOS 11, which is provided by System Keychain as well. And there is a specific case named iCloud keychain where you could share certificates, passwords, and so on between several devices. Okay, a brief overview of Common Crypto API. Common Crypto, as I said previously, contains different functions using for hashing and for message authentication code creation and for encryption. Okay, unfortunately these classes are not available on the Apple developer portal officially, so you have to use man pages for that. You should just put in man ccrypt, ccmd5, cc-sha, cc-hmac, and cccryptor. The main class here is the cccryptor because it allows you applying bulk ciphers. But if you want to have a one-shot encryption, there is a special function named cccrypt, where you supply an algorithm, the initialization vector, and the number of iterations if possible. So cccryptor supports DES, triple DES, and IIS ciphers, but only IIS is recommended in the modern applications. cc-hmac is used for message authentication codes, so you could apply it to an already encrypted data. Then you have ccmd and cc-sha hash functions. Only SHA-2 family is recommended for usage nowadays because all the others are vulnerable to different rainbow tables attacks. And there are a number of other minor security APIs, but I would like to mention the most important of them. The first one is the key stretching or key derivation function, also known as PBKDF2. It allows you to create a data encryption key using a password. So you just supply the number of iterations, the initialization vector, and the original non-encrypted data to it. And then it produces a vector of bytes of particular length, which you may use as the data encryption key. The second one is the sec-random copy bytes. That is the interface for a secure enclave contained pseudo-random number generator. Actually, it proxies dev-random or dev-urandom. And this is the only pseudo-random number generator which should be used in cryptographical applications. Just forget about random, arc4random, srand, and so on. They could be used for some sort of things like array shuffling or image shuffling, but not for cryptographical purposes. And the SSL context reference. As I mentioned before, this is an API for managing legacy SSL 3.0 and TLS 1.0 protocols. It should not be generally used. It may be used in legacy applications only. You could see a specific test which is run for pseudo-random number generators, so-called stellar sky. So you have the black surface, and the pseudo-random generator distributes a white point in case what it generates. So a good pseudo-random number generator has no patterns inside such an image. It is like a Gaussian white noise you may see on the TV when you are tweaking it. However, this is not a good generator because you can see stripes and some repeating images here. So such a generator could not be used in cryptographical applications. Okay, let's look briefly how the TLS and the network layer protection works. This is a common situation. It is a triple TCP handshake, and then the TLS connection establishment. So after triple TCP handshake, we are trying to establish the secure connection. We are sending client hello message. The server gives us the set of supported cipher suites. Sorry, not the cipher suites, but it gives us its certificate and starts generating the private and public key pair. Then the client chooses a cipher suite which is available on the client, then changes the cipher spec, generates its own pair of public and private keys, gives the public key to the server. The server calculates the master encryption key and derives session keys. Session keys have about 1 hour of lifetime, and they are refreshed using the same mechanism. So they are regenerated using the public key cryptography. After the TLS handshake has succeeded, you can transfer your secure data. What is the most compromisable thing in this scheme? It is, of course, the validity of client and server. The client should know that the server is the actual server, and the server should know that the client is actual client. So, as it is called in cryptography, Alice should know that Bob is Bob, and Bob should know that Alice is Alice, and not the Mallory who is trying to eavesdrop their connection. That's why we have so-called certificate chains and lists of trust. Each operating system comes pre-bundled with a set of root certificates. These certificates are provided by the certificate authorities, which contain these certificates' private keys. All the certificates are implicitly trusted by the system. So, if a certificate is signed using a valid certificate's private key, then this certificate is also considered valid. So this algorithm recursively works until the leaf certificate is matched, or vice versa, until the root certificate is matched, if we are going from the site certificate to intermediate and to the root CA. Unfortunately, as you may know, system administrators and all power users have the ability to change this list of trust and to install self-signed certificate. Okay, most modern operating systems support installing it, but they do not trust them implicitly. To make the operating system to change the trust settings, you should explicitly sign that this certificate is a root trusted certificate. It is valid for most modern Windows distribution, macOS distributions, and iOS as well. If certificate's private key is stolen, it means that someone could use it to decrypt the contents of your network connections, or to have the same patched certificate produced using the same private key. However, there is a special procedure named certificate revocation when the certificate authority revokes that certificate and makes it invalid. Operating systems also support certificate revocation procedures using one of 3 modern methods. The certificate revocation list, when the system downloads a full list of revoked certificate. Then online certificate status protocol, when the system asks for a particular certificate, and so-called OSCP stapling, when the certificate authority returns a signed non-CA sent by the client, indicating whether the certificate is valid or not. So there are 3 basic procedures of checking the certificate for revocation. All these procedures are used in the app transport security mechanism. This mechanism is switched on by default on iOS 9 and above, and it forces the developers to follow security best practices, namely using HTTPS everywhere. How we could check the applications or the endpoints for ATS readiness? There is a special built-in NSCURL utility inside the macOS 10.11 and above, or using the flag name CF Network Diagnostics equal to 1 for iOS applications. The requirements for an ATS compliant connection are the following. These are mainly for the server. First of all, leaf certificate should be signed by a certificate, which is signed by a certificate, which is signed so on and so forth, until we have the CA certificate. So the first thing, the CA certificate should be from a trusted authority. The second one, minimal TLS version should be 1.2. No exceptions. Then non-compromised cipher, IS only, should be used for connection encryption, and SHA-2 family of hashes should be used for message authentication codes. The third requirement, it is the RSA with a long key like 2048 bits, or elliptic curve digital signature algorithm with the 256 bits used for digital signatures. during the handshake and certificate validation. And the final requirement is the perfect forward secrecy of the cipher suite. The only key exchange protocol in iOS which is capable of providing such a requirement, which is compliant with such a requirement, is the elliptic curve Diffie-Hellman ephemeral key exchange. That means that we have only 10 or 11 cipher suites, the most powerful cipher suites at the moment in the world, which are allowed by default. So you see that the first is the protocol, the second is the key exchange scheme in cipher suite, elliptic curve Diffie-Hellman ephemeral. Then the third one is the digital signature algorithm for the certificates. It is elliptic curve digital signature algorithm. Then we have the encryption, IAS 256 and Galois counter mode, and the message authentication code SHA-384. If we disable the perfect forward secrecy requirement, then we will have so-called pre-master secrets generated during the TLS handshake, and we will be able to use 6 more cipher suites. However, if we are in transition period or we are working with the legacy servers, we could configure some exceptions. The first thing is that we should try never allow arbitrary loads for all connections. However, if we've set up such a thing, we may configure ATS exception in reverse order, so we could allow application go everywhere and be not ATS compliant, but find out a domain which is bound, let's say, to our APIs, and configure ATS exception like TLS 1.2 for that particular domain. Or we could do the thing vice versa. We could disable going everywhere and enable loading all contents even via HTTP for a particular domain. This might be useful if you have a local server which is identified not by the domain name but by the IP address. You could also configure this for web or media content and for different things like including or excluding subdomains or including and excluding minimal TLS version. However, if ATS is disabled, some standard TLS checks are still performed. You may know them if you're familiar with the certificate validation procedures and with the certificate or public key opinion procedures. Each time you connect to remote server via HTTPS, your NSURL session receives an authentication challenge, and it usually has the UNS protection space configured with the server trust method, and you receive the certificate data. That is what we have on the TLS handshake step. The algorithm is pretty simple. We just have this certificate data. We set the policy and we validate the certificates received from the server via the policies. We could use standard X509 validation procedure which is performed by default. However, this is vulnerable when you have some self-signed certificates installed and trusted. Then you could use lightweight pinning, so validating the hashes or pins of the certificates. They should be hard-coded in the application somewhere. And you could use heavyweight pinning when you validate against the certificates which are included in your application's bundle. This is a common measure for banking applications. They usually validate that because they are dealing with money. You could also use certificate revocation policies. They will indicate that your certificate is not valid if you are trying to connect via proxy server and the proxy server certificate is installed on your device. Then you just call sectrust evaluate method or its asynchronous version and check the result. It should be either proceed or unspecified. All the other cases are not valid. You should terminate the connection. Yeah. Well, actually, if you are talking about the certificate pinning, yeah. You could use OpenSSL command line and download the certificate in PEM form, convert them to their form, and embed them into the applications bundle. Then you will be able to use them programmatically, load them as raw data, and submit them to the crypto API. So you may not bother your customer, your client to provide the certificates. However, sometimes they provide the certificate suits by themselves. So it's a pretty standard task. You use OpenSSL. You may use, as far as I remember, there was such a feature in Chrome, then it was removed, but it's still available in Firefox to download the certificate of intermediate, whether it is a root intermediate or leaf certificate.
One more question. For example, in Bulgaria, we have several, like 4 or 5 certification authorities, which issue the so-called CAP, which identifies the person, your personal ID there.
Okay.
But they issue it on a USB device. Can you invoke such a certificates for mobile devices?
Well, I have never. The question was about the using the certificates from a USB stick on the iOS devices. Unfortunately, I've never been working with such a such a thing. However, I know that most of these USB sticks are vulnerable to extracting this private key and certificate. So if you use such a vulnerability, you will be able to steal such a key and certificate from a USB stick and use them as you wish in any application. However, that is not quite legal.
Yeah, you should not extract because you
Yeah.
should use a
Unfortunately, then the USB stick is designed for usage on big computers only, not on the laptop. Sorry, not laptops, but not on the tablets and phones. Unfortunately, this is the limitation.
В Safari помощь ставишь ваша сайт
Okay.
if you like to use your
Okay, and a brief overview of several recipes. Please keep patient. There is only 10 minutes left.
Okay, sorry.
Okay, so how we could secure our cache data? We can use any kind of data storage, whether it is SQLite, Realm, core data, and so, or just plain files. But we could use raw encryption. However, if we use core data, there is no, I see no objections in using value transformers. They are designed specifically for that. So you have a property, you have a value transformer attached to this property, and you register this value transformer using a key. So this value transformer does all the cryptographical stuff for you. You just subclass it, you prepare the encryption model here, and you use this module inside the application's code. The alternative is transit properties. So these properties are actually reflected in core data model editor, but they are proxying some other properties which contain raw data. The main drawback of such method is that you won't be able to use full text search on string fields. You will need to decrypt them and to use full text search in memory, not SQLite's embedded full text search. The second option, if you use SQLite, you should use SQL Cipher or SEE extensions. Both are recommended by the creator of SQLite. You just need to submit a special encryption key into the model, and that would work like a charm. The same is valid for Realm. Realm has built-in encryption capabilities. If you're using any kind of file, you may use the file protection classes, and this might be sufficient. But if you're paranoid, you may use the direct IS encryption. You want to open an encrypted stream via a encrypted data provider and write the encrypted contents on the disk. If you want to save credentials, the only valid way is saving them encrypted, hashed, and salted in keychain. What I mean here, so let's say we have a special case. We need to store a local passcode. So let's say our passcode is 1, 2, 3, 4. We encrypt it, or we use the pbkdf2 function. We're saving the name of the function. Then we save the number of iterations, let's say 10,000. Then we save the initialization vector. And then we save the actual hash. What does this format help us to do? It helps us to migrate the number of iterations, the algorithm, or the initialization vector without any consequences. This is the simplest way. Oh, okay. Let's move this so it is available. The same thing is valid for different value transformers. You may use the same format. Let's say you are using AES 256 GCM, then you use the particular IV, and then here is the encrypted data. It allows you migrate into another cipher, because different countries have different regulations in the cryptography sphere, and one cipher which may be useful and which may be applicable, in one country may not be approved in the other country. You know that European Union had some objections when iOS was released. They wanted to have ciphers like Salsa 20 to be included into the standard distribution. Okay. I will hide a bit. The other way of doing this is using steganography. So it is a special area of information security which studies how to hide the fact of encryption. Let's say you have an image of a cat. You change only the last bits of each pixel. This won't affect the coloring so much, but you will have the same cat image, which is almost indistinguishable from the original one, but there will be a password or a key. Okay. How to deal with web views and how to deal with cache and web contents. Unfortunately, I've almost never seen the valid configuration of HTTP cache and headers, especially for authentication requests, which should use no cache, no store. Because default policy in iOS is use protocol caching policy. Regarding the web views, we have tough choice right now. We have 3 different web views: UI web view, WebKit web view, and Safari view controller. Good old UI web view, well, I would not recommend using it anymore because it is considered as insecure. It has several vulnerabilities related to JavaScript and path traversal attacks. Modern WebKit web view is generally more secure, however it has some drawbacks, but it is generally safer due to the fact that it is running as an external process and you are using actual inter-process communication APIs. And Safari view controller, this is the most secure because it requires no app transport security tweaks. However, the only drawback is that it supports GET requests only, but that can be you can have a hack like a locally running web view to redirect GET to post and so on. Then as I said previously, we should configure cache and headers wisely. Using no cache, no store for authentication headers is a must. Sorry, not for authentication headers, but for authentication calls like token calls, username, password calls, and so on. The third measure is URL cache and cookies. You should clean them, even if the protocol's policies are configured wisely, just to be just to be absolutely sure, just to double check that nothing essential or nothing critical is left in the storage after you've logged out or after a session has been terminated. Well, how to derive a good encryption key? As I said previously, password-based key derivation function is used for stretching passwords, for creating hashes of passwords, and encryption key for passwords. Actually, I was lying a bit, because you should never use directly. You should never use it directly, because it produces lots of problems like password changes, when you change the password, your data encryption key, which would change it, you will have to re-encrypt large volumes of data. You should also never caching this value in memory and use it only on demand. What should we do? The best practice here is described as 3-2-1 principle. The best key consists of 3 parts. 2 of them are related to what you know and what you have, so-called two-factor authentication, and 1 of them is never stored on the device. It can be stored on the server, on the external media, but not on the device itself. Then you should use as many iterations of password-based key generation function as possible. User experience says that it's better to use around 10,000 or 20,000 iterations. Then, if you want to have good passcode, you should use graphic patterns like it is done on Android, or secure pseudo-random number generator like sec number, copy random bytes. Then, it is also worth splitting the arguments of your key generation function and storing them in different places. And finally, you should use salt to make it even harder to decrypt or to crack the key. If you add even a small salt, the entropy is enlarged exponentially and the key would be absolutely different. It also prevents you from different hash collisions. Okay, how to build a secure authentication scheme. First of all, do not transfer passwords, if possible, unencrypted, weakly hashed, or hashed few times. It means that, okay, we may use things like form authentication, but only in case we're absolutely sure that our transport channel is secure. The second is related to session IDs. Prevent stealing them and prevent the session fixation attacks. That means that you should use tokens or session identifiers with a limited lifetime. And they should also have explicit expiration time. Then these tokens should be stored securely, as I mentioned before, in keychain, the best place for that. Even if a request has been intercepted by a malefactor, especially if it is a banking application, you should use some measures to prevent reply attacks. So the best measure here is to use digest authentication and non-C values, which are unique per request. It means that the reply attack would fail and you will receive the invalid HTTP code. Also, you should also let users identify which locations are trusted. For example, if you are sitting here in Bulgaria and you see some suspicious activity related to your account from somewhere in India or in United States, you should receive a security alert. It means that someone is trying to hack you. It's a common measure, however, it has some drawbacks. For example, the common drawback is the security service of banks when they are trying to block your credit card when you are in another country and you move too fast. However, you should warn them in such case. And you should supply only generic information about the failed login and password or the failed password recovery. You know that some applications use, when you provide an email for password restoration, inside the password restoration form, they say, oops, we have no such account. It means that such applications are vulnerable to login enumeration. If we have a database of email accounts, then we could try using them one by one, and we could identify which emails are registered in this system. The best security protection measure here is to use a generic message like which says like, an email has been sent to your account, please wait. And it doesn't matter whether this is a valid or invalid account. The same is for login screen. Invalid username or password is the best friend in such situation. Okay, and something more which is related to jailbreak. If you want to prevent debuggers from attaching to your application, you should use ptrace functions. Then, pasteboard and snapshots which are done by the system. You know that system does a snapshot. And you may also know that some applications like banking applications, insurance or health applications also blur the screen contents while you're going to background. This is a valid security protection measure against side channel data leakage. If your device is jailbroken, a malefactor could steal the snapshots, and if you have a password input field with the view password functionality, then this password may leak. You should also use two-factor or multi-factor authentication. The most reliable second factors as this year are push messages, code generation applications, hardware tokens, and API keys. Why not SMS? You know the signaling protocol 7, SS7, is vulnerable. So a person who is familiar with SS7 vulnerabilities may intercept your SMS message. So SMS short messages are not secure anymore. They should not be generally used as the protection measure as a second factor of authentication. They may be used as a side channel of notifications, but not as a way of delivering the second factor. You should also lock the application and terminate the session locally after a predefined idle timeout. Usually it is set from 5 to 10 minutes or maximum 15 minutes. And the final measure, the best thing a security researcher and a security coder should remember. It's better to protect against particular threats rather than improve the security level, the overall security level, because you should mitigate the most probable threats. You should prevent the most probable attacks, and all the rest can be done further. Okay. The final note is related to submitting crypto applications to the App Store. If you are using the crypto security SDK, this is fine. You should just tick some marks in the App Store. If you are using third-party implementation of encryption like SSLs, OpenSSLs, ciphers, or your custom written ciphers, you should try finding an implementation, an IRM-optimized implementation for them. This is the first. And the second, you should provide a CCATS compliance certificate. It is received in the United States only, and this is a long procedure which might take up to 45 business days. Please remember that even if you are using HTTPS, you have to tick yes inside the App Store when you're trying to submit the application. If you have some issues related to the encryption, to rejection of cryptographic apps, you should contact not Apple review team but Apple support directly. This is a recommendation from several people who faced several issues related to cryptographic apps. Not Apple review team, but Apple support, Apple development support. They will react much faster. So, what can we read further about the security on iOS? Here is a set of WWDC sessions related to data encryption, to security overview on iOS, to secure data storage. There are some links like iOS encryption, iOS developer cheat sheet on OWASP portal project, link to public key cryptography standards, and well, I think that the best source, even this might look a bit outdated, is Jonathan Zdiarsky's book, Hacking and Securing iOS Applications. The first part of this book is dedicated to how to crack the applications, while the second says how to protect from being cracked. And some more links. There are lots of different links related to server trust evaluation, technical note from Apple, server trust validation, the blog of Jonathan Zdiarsky, how to perform penetration testing of iOS applications, and so on and so forth. So thank you for being patient. I'm waiting for your questions. Yeah. As far as I remember, it is synchronized in the same way as it is done on the key generation applications like Google Authenticator, Microsoft Authenticator. You just provide the valid timestamp. This is the essential. And these pseudo-random number generators use the same seed based on the timestamp. That's the way how they synchronize. And most of the key validation algorithms which are used on the server side and on the client side for checking the validity of certificates use system timer as well. You know, there might be some issues related to invalid OpenSSL. If you have your clock set up for 1 day after tomorrow or the day before tomorrow or a year and so on. And what is more important, Diffie-Hellman and Kerberos are using system timers as well. Yeah.
Is it possible to use kind of a token to lock
Sorry, to lock a phone?
to encrypt the phone?
Well, unfortunately not for iOS. I think that Android may have some capabilities for that, like specially crafted hardware, but not for iOS. Maybe, well, if you explore some kind of private undocumented API and you are eligible for MFI program, manufactured for Apple, then you have some extended rights and you have access to some hardware features which are not available in usual mode. Then it's worth trying, but in general I think it is not possible. It's just a second factor. It is another evidence that you are you and you have this. You know your password, you have the token. You know the key, you have the push message on your phone. If one of these factors is removed, then the scheme is not working. Let's say you've lost your phone, but you know the password, then you couldn't authenticate. That is the idea of MFA. Any other questions? Yeah.
Please, you mentioned that in order for the keychain sharing to work, the team ID needs to be the same. Does that mean that if an app is transferred to another user, it will stop working?
No, no, it doesn't mean that if we try. Sorry, what kind of user? You mean the Apple Developer Portal?
Apple developer from China.
Yes. Then it might stop working, unfortunately. You just need to change this ID simultaneously, but you will lost the old records. So you just need to back up them beforehand. Otherwise, they will be lost if you migrate from one account to another. Okay, if there are no more questions, thank you all again for coming here today.